Hey bud, what's got you all worked up?
Just this gosh darn statistics review. Ugh, it's got me really worked up. The test is tomorrow. I don't know what I'm doing. I just want a nice, refreshing glass of water.
Well, don't you worry, chum. I know a thing or two about statistics. Why do you think I'm a bartender?
Alright, how about you take a look at this problem? I'll put it up using my, special popularized hologram projector, but I'll also read it in case you're illiterate. So basically, there's 9 sales representatives, 6 of which are men and 3 of which are women, and they work at a small company wanted to attend a national convention. There were only enough travel funds to send 3 people. The manager selected 3 people to attend and stated that the people were selected at random. The 3 people selected were women. There were concerns that no men were selected to attend the convention. So part A of the problem is to calculate the probability that randomly selecting 3 people from a group of 6 men and 3 women will result in selecting 3 women. Part B is based on the answer in part A, is there reason to doubt the manager's claim that the 3 people were selected at random, and then explain that. And then part C is that an alternative to calculating the exact probability is to conduct a simulation to estimate the probability. A proposed simulation process is described here, as each trial in the simulation consists of rolling 3 fair, 6-sided dice, 1 die for each of the convention attendees. For each die, rolling a 1, 2, 3, or 4 represents selecting a man, rolling a 5 or 6 represents selecting a woman. After 1,000 trials, the number of times the dice indicates selecting 3 women is recorded. Does the proposed process correctly simulate the random selection of 3 women from a group of 9 people consisting of 6 men and 3 women? Explain why or why not. So if you think you can do that problem, go right ahead.
This is an easy one. You see here, use the multiplication rule. So basically, let's see here, you're going to take the probability that the first is a woman times the probability that the second is a woman versus the probability that the third is a woman. And that's of course given, that the second one's a woman and the first is a woman. So it ends up being 3 over 9 times 2 over 8 times 1 over 7, which is 1.2%. And then, the probability calculated in Part A does provide a reason to doubt the manager's claim that the selections were made at random. That is because of the 1.2% chance that random selection would have resulted in 3 women being selected. The probability is small enough that it may cast doubt on the manager's claim that the selections were made at random. And for Part C, the answer is no. The process does not correctly simulate the random selection of 3 women from a group of 9 people, of whom 6 are men and 3 are women. The random selection of 3 people among 9 is done without replacement. However, in the simulation with the dice, the 3 dice rolls at any given trial are independent of one another, indicating a selection process that is done without replacement.
Wow, that actually makes a lot more sense now. Thanks for the help.
Any more?
Yeah, there's a couple more. You can have a look at them, I guess.
Well, I'm not good at these, but I know a guy. Come on, dog. Hey, pool master.
Yo, what's up, chump? You ready to pay up the money you owe me?
Nah, man, I don't got any cash on me. I'm here helping this bucko here. He needs you to explain his second problem.
Okay. Sorry, I had a little thing going on. Anyways, so alright, so this problem is that each full carton of grade A eggs consists of one randomly selected empty cardboard container and 12 randomly selected eggs. The weights of such full cartons are approximately normally distributed with a mean of 840 grams and a standard deviation of 7.9 grams. So part A of the problem is what is the probability that a randomly selected full carton of grade A eggs will weigh more than 850 grams? Part B, The weights of the empty cardboard containers have a mean of 20 grams and a standard deviation of 1.7 grams. It is reasonable to assume independence between the weights of the empty cardboard containers and the weights of the eggs. It is also reasonable to assume independence among the weights of the 12 eggs that are randomly selected for a full carton. Let the random variable x be the weight of a single randomly selected grade A egg. And then B, part I, is what is the mean of x, and B, part II, is what is the standard deviation of x.
Alright, I guess I can help. Just don't tell the cops I was here, alright?
Of course, I got you, bud.
Now pay attention, fool. Alright, fool, let's see here. Now, you're gonna wanna have to find a z-score for this one. You're gonna take that A50 you're looking for, minus that mean A40, put that all over the standard deviation 7.9. That's gonna give you the z-score of 1.27. Then, you're gonna use your table to find that equates to 8980. 0.8980, mind you. Then you're gonna do 1 minus that to get 10.20% for your P. Now for part B here, let's take a look here. Alright, so all your eggs have the same variance of weights. So your formula ends up being the variance P plus 12 times the variance of XI. Now since you're trying to do it for a whole dozen worth of eggs, your variance of P ends up being that 840 minus 20 over 12, which gets you 68.33 grams, right? And your variant W, alright, I'm just going to start over here. I'm just going to read it and see. So we're going to let W represent the weight of a randomly selected full egg carton, P, the weight of the packaging, XI, the weight of the egg, for I equals 1, 2, and all the way on to 12. Now let's note that our formula here is W equals P plus X1 plus X2 plus etc. till we get to X12. And the property of its expected values establish that E of the W equals E of P plus E of X1 etc. to E of X12. Because all 12 eggs have the same mean weight, this becomes EW equals EP plus 12 times EXI. Since we're told that EW equals E40, it's 840, and EP equals 20, we can solve. So now, 840 equals 20 plus 12 times e to the xi. And to find e to the xi, you take that 840 minus 20 over 12, and you get 68.33 grams. So, we're told that our standard deviation of W is 7.9, and the standard deviation of P is 1.7. So therefore, variance of W equals 7.9 times times itself, so it's squared, and that equals 62.41. And variance of P is 1.7 times itself squared, so that's 1.7 squared equals 2.89. So now we can solve 62.41 equals 2.89 plus 12 times the variance of xi, and then to find the variance of xi, we do 62.41 minus 2.89 over 12 equals 4.96. Therefore, the standard deviation of xi is the square root of 4.96, which is 2.23 grams.
That's great, and thanks for the help, but I still don't get this last problem. Is there anyone else you know that could maybe help with it?
You sure, pal?
If I don't pass this test, my life is over.
Well, dying is dying, I guess, no matter how you do it. Come on, bub. I got one more guy up my sleeve. Hello? Is anybody home?
Blarg! Who dare disturbeth mine slumber?
Take it easy, Buster. We just want to ask you a couple statistics questions.
They told me you would come. They told me. Fine, I am in no mood to argue with the gods. What's the question?
Ask him, dummy.
Here, this one. So, a researcher conducted a medical study to investigate whether taking a low-dose aspirin reduces the chance of developing colon cancer. As part of the study, 1,000 adult volunteers were randomly assigned to one of two groups. Half of the volunteers were assigned to the experimental group that took a low-dose aspirin each day, and the other half were assigned to the control group that took a placebo each day. At the end of 6 years, 15 of the people who took the low-dose aspirin had developed colon cancer, and 26 of the people who took the placebo had developed colon cancer. At the significance level 0.05, do the data provide convincing statistical evidence that taking a low-dose aspirin each day would reduce the chance of developing colon cancer among all people similar to the volunteers?
I'm normal. I always knew they would send me this problem. I can do it, no issue, tissue. Now for this question, we're going to use a phantoms test. So to start, you're going to list out your P1, which is the proportion of people who took low-dose aspirin and got cancer, and your P2, the proportion of people that took the placebo and got cancer. Then you list your hypotheses. P1 minus P2 equals 0 is your null, and your alternative is P1 minus P2 is less than 0. Now the name of the test is a two-sample t-test, and your assumptions and conditions are random and large enough. We know that it's random because it states so with the question, and we know that it's large enough because 15 out of 500 and 26 out of 500 are both large enough. Now to find your test statistic, you're first going to combine your two groups. Doing so is 15 plus 26 over 500 plus 500. This ends up being 0.041. Now, you continue finding your test statistic by taking 0.030 minus 0.052. This is all over the square root of 0.041 times, in parentheses, 1 minus 0.041, close parentheses, times, once again, in parentheses, 1 over 500 plus 1 over 500 in parentheses. This ends up being negative 1.75. Now to find the p-value, you're going to take the probability that z is less than or equal to negative 1.75. This is 0.0401. Now, the conclusion is that because the p-value is less than the given significance level of alpha equals 0.05, we reject the null hypothesis. The data provide convincing statistical evidence that the proportion of all adults similar to the volunteers who would develop colon cancer had they taken low-dose aspirin each day is less than the proportion of all adults similar to the volunteers who would develop colon cancer had they not taken a low-dose aspirin every day. Essentially, that means that your alternative is true, that P1 minus P2 is indeed less than 0.
Wow! Thanks!
Now get me out of here! Tell them to free me!
Let's get out of here, Scoob.